So in the last class, we discussed about tensors. Today we are going to discuss about pseudo tensors. So we already studied that tensors are defined by coordinate transformation under rotation. For example, in the case of a simple tensor or the tensor of rank 1, that is a vector, will be transforms like this: xi dash is equal to aij xg, or ai dash, or in general ai dash is equal to aij aj. So this rotation is one type of transformation. There are another type of transformations also. They are reflection and inversion. So in the case of inversion, the coordinate will be uh, coordinate the coordinate changes sign. That is, x is changes into minus x, y will changes into minus y, and z into minus z. Or in general, this in the case of inversion, this aij, in here aij is this term. So aij is equal to minus delta ij. We know that delta, if I is equal to j only, this delta term exists and its value is 1. Here aij is equal to minus delta ij means when I is equal to j, this quantity become minus 1. So this transformation equation will changes like this: xi is equal to minus xi dash. So this is an example of inversion. So this is in the case of inversion, its coordinate changes into minus of the original coordinates. If original coordinates are x1, x2, x3, new set of coordinate or transformed set of coordinate will be minus x1, minus x2, minus x3. So this is an example of inversion or parity transformation. So in the case of inversion, we will change the coordinate into to a minus of that. So under inversion, the right-handed coordinate system become left-handed coordinate system. So if a transformation changes the right-hand coordinate system into left-handed coordinate system, it is called inversion. We can define pseudo tensors in terms of inversion, and also we can define pseudo tensors in terms of reflection also. There are two types of vectors, or in general tensors. Normally we can call there are two type of vectors, that is polar vectors and pseudo vectors. Or in general we can call there are two type of tensors, that is polar tensor and pseudo tensor, or this pseudo tensor otherwise called axial tensor. In special case, this is axial vector. Okay. So tensors are generally divided into, or vectors are generally divided into two types. First one is polar vector. Second one is pseudo vectors. Or in general, in terms of tensors, there are two types of tensors, that is polar tensors or pseudo tensors. Pseudo tensors otherwise called axial tensors. Okay. So they will transforms. This classification is because they will transforms in different manner under inversion and reflection. The transformations under reflection and inversion are different. In the case of rotation, the transformations are same, but in the case of reflection and inversion, their transformations are different. According to that difference, we can classify tensors into polar tensors or polar vectors or axial vectors. Axial vectors otherwise called pseudo vectors. They are called axial vectors. One example for polar vector is our position vector. So this is a position vector. This is a prototype of this polar vector. Its component is x1, x2, x3. Instead of x, y, z, we are using x1, x2, x3. So after inversion, its component will be, this is inversion, x1 is changes into minus x1 dash, x2, x1 changes into x1 dash, x2 changes to x2 dash, x3 changes to x3 dash. Or after inversion, this x1 dash is before inversion its component is x1, x2, x3. After inversion its component is x1 dash, x2 dash and x3 dash. But when we look at these two figures, we know that x1 dash is nothing but minus x1, x2 dash is nothing but minus x2, x3 dash is nothing but minus x3. So this is change, this is the transformation of its coordinate. So in the case of polar vectors, if their components transforms like this manner, they are called polar vectors. The position vector are and all type of vectors whose components transforms like this is known as polar vector, or they have an odd parity. Odd parity changes its component, changes its sign, not the vector but its components. We are discussing about component of a vector. So the component changes like this is known as polar vectors. They have odd parity. There are another type of vector which can be written as the cross product of two polar vectors. For example, suppose we have a C vector that is equal to A cross B. Then these type of vectors, for example, the vectors like C is known as pseudo vector or axial vector. Okay, let us examine how its components transforms in inversion. Okay, its components, its component is given by ci. General component can be written as ci, maybe c1, c2, c3, just like a1, a2, a3 or x1, x2, x3. So we can examine how its components, not the vector, or its components transforms in inversion. Or we already discussed about the cross product. So C1, the first component of the vector C1, its second component C2 and third component C3. So C1 transforms like this: A2 B3 minus Y component Z component, Y component of A and Z component of B minus Z component of A into Y component of B. That is A C1 is equal to A2 B3 minus A3 B2. We already discussed this during the vector analysis. Okay, how this will how this first component C1 uh, arrived in this way. That things we already discussed in our first chapter. So its component, suppose it transforms under inversion. So what happened? A1, A2, B2, A and B are polar vectors. So in general, AI after inversion will become minus AI dash, or AI dash is equal to minus AI. Both are same. Or BI dash is equal to minus bi, or bi is equal to minus bi dash. So how will ci dash transforms? This is ci dash transforms like this. We know that C1 is equal to A2B3 minus A3B2. Similarly, C1 dash is equal to A2 dash B3 dash minus A3 dash B2 dash. What is A2 dash? It is nothing but minus A2. What is B3 dash? It is nothing but minus B3. So we can write this minus A2 minus B3 minus of bracket A3. A3 dash become minus A3 because this is a polar vector. It transforms like this. And B3 B3 dash is minus B3. It's component of B. Okay, it is transforms like this. It is also a component of polar vectors. So this minus and minus become plus. So this is A2 B3 minus A3 B2. So it is nothing but C1. So C1 dash is equal to C1. C1 and C1 dash are the component, not the vectors. So the component of a vector C does not transforms like a polar vector under inversion. So this type of uh, vectors whose component transforms like this way is known as pseudo vectors or axial vectors. In general, we can say these axial vectors have even parity. Example for axial vector is angular velocity B is equal to omega cross R, orbital angular momentum L is equal to R cross P, torque can be represented by N or tau. In some book it is notated by N, or in Afghan it is notated by N. Normally it is represented by tau. It is R cross F. Or magnetic induction field dou B by dou T B transforms like this. Dou B by dou T is equal to minus del cross E. Here in the case omega, in this case in the case of an angular velocity, v is equal to omega cross r. We know that v is equal to nothing but dr by dt. R is a polar vector, so v is a polar vector. So v and r are polar vectors, so omega should be a pseudo vector or axial vector. In general, angular velocity is a axial vector. We can write its transformation like this. So this is x y z. It is transforms like this: x dash y dash z dash, and this rotation changes. This is rotation in this direction. It changes like this. Okay, normally the vector changes, okay, but its component does not changes under inversion. Okay, now we will discuss only in terms of its component. We are not bothered about the vectors. Anyway, this transformation is like this. Okay, so now we defined polar vectors and axial vectors. Axial vectors are otherwise called pseudo vectors in terms of inversion. Now we are going to redefine these polar vectors and axial vectors in terms of reflection. Okay, we can distinguish between uh, axial vectors and polar vectors in terms of inversion and reflection. We already discussed about inversion. Now we are going to define polar vectors and axial vectors in terms of reflection. So the distinction between polar vectors and axial vectors can also be illustrated by reflection. A polar vector reflects in a mirror like a real physical arrow. So this is reflection. Suppose a mirror is in the xz plane, and here P is a vector. When it reflect in this mirror, that mirror is in the xz plane. This P dash is its mirror reflection. So here is the reflection of here in reflection the coordinate axis remains fixed. The world or the physical quantity reflect as a mirror in the xy plane, sorry, mirror in the xz plane. This is so mirror here, this is the xz plane is taken as mirror. It's one image is p dash and another image is p, one image is p, another image is p dash, is the reflection. So when we observe the component of p which transforms under this reflection, we can we can easily say that here p, the reflection is in the plane xy xz plane, so not xy plane, it is x plane. In the case of p, this px and pz will not change under reflection, but the py changes its sign. Here py changes into minus py. So we can write its component like this. For mirror index y plane, py become minus py. So the component p is equal to px, py, pz. It changes into p dash is equal to px minus py, pz. So this type of transformation, the vectors which transform this type this way is known as polar vectors. For example, this displacement vector, velocity are example of polar vectors. But there are another type of vectors as we discussed earlier, the magnetic field, torque, etc., or magnetic moment behave quite differently under reflection. We can take the example of magnetic moment mu, which produced due to the circular motion of electron. So this can be drawn by this. This is this is this is also we are taking a mirror in the xz plane. So this is our mu. It's magnetic dipole moment. So its direction is like this. Its mirror image will be like this. Okay, it will not transforms like polar vectors. In the case of polar vectors, only one coordinate changes. But in the case of in this case, this is known as axial vectors or pseudo vectors. Mu is equal to, normally the coordinate mu is given by mu x, mu y, mu z. After reflection, it becomes mu dash is equal to minus mu x plus mu y minus mu z. Okay, so it transforms like this in reflection is known as the axial vectors or pseudo vectors. In general, we can say that the quantity which transforms like this is known as pseudo tensors or axial tensors. We are taking the example of vectors and we generalize into the case of tensors because vectors are a simple uh, order 1 tensor, rank 1 tensor. Okay. So from the above transformation, it is clear that we cannot add any axial vectors to polar vectors. If two vectors are equal in a vector equation, if A is equal to B, A and B should either polar vector or axial vectors. So in the case of vector addition, the two vectors should be axial or polar. Then only it can be added. Okay. So this can be generalized into the case of tensors also. So we can say that a type of tensors as pseudo tensor. Uh, we can define pseudo scalar, pseudo vectors, and pseudo tensors. We can define the pseudo scalars are the scalars which transforms like this in inversion or reflection or in general transformation. In any transformation, the pseudo scalars transform like this, that is s dash is equal normally s dash is equal to s. Here s dash is equal to a determinant of a into s, or in general a pseudo vector transforms like this. Ci dash is equal to normal transformation is Ci dash is equal to aij cj. In the case of pseudo vectors, Ci dash is equal to a determinant of A into Aij, Cj, or in general, a tensor transforms like this, tensor of rank 2, A dash Ij is equal to determinant of A, Aik, Ajl into Akl. We already discussed about transformation of tensors. So there is an additional term for pseudo tensors, and this can be written as this determinant's value is like this. In the case of inversion, the value of determinant is minus 1 0 0 0 minus 1 0 0 0 minus 1. Its value is minus 1. In the case of reflection, the determinant value is minus 1 0 0 0 1 0 0 0 1. In the case of if the reflection of one axis, that is about x-axis, reflection in x-axis. So normally we discussed reflection in y-axis. Here we are taking reflection in x-axis. So its value is minus 1. And in the case of pure rotation, this value of this determinant is become plus 1. So we will get the normal transformation equation in the case of rotation, because in the case of a pure rotation, the determinant value is plus 1. So that about pseudo vectors, tensors, and scalars.